one of the most difficult sections to understand in this chapter, variation and application. We're going to talk about situations that involve direct variation, and we're going to talk about situations that involve inverse variation. It's really the two that you have to keep straight. First, we're going to talk about direct variation, but I'd like to give you an example of a situation. If, and I've already used this example once before, if I were to work at a pay of $7 per hour, and I worked for for 5 hours, I would get paid $35. However, if the week after that, $7 an hour, and I worked 11 hours, I would get paid $77. As my input, the number of hours that I work, goes up, my output, or the dollars that I get in my paycheck, goes up as well. That's called a direct variation. And a direct variation is defined by the equation y equals k times x. In the situation that I just gave you, I would say to you that my input is my 5 hours, and I'm going to go ahead and use this as an example. My x value, and I'm going to state that let's let x equal 5, and my output in one of my examples was I earned $35, and so what I want to do is find my, I forgot what the letter, variation constant, I lost track of my variable. K, the variation constant, I want to find out what that's equal to. I substitute in the $35, I substitute in the $5, that's my independent variable. I get to choose how much I make each week, that's why I put that in for x. And again, I put in 35 for y. I'm going to solve this thing for k, and I'll find out that k is equal to 7. That's the $7 per hour that I'll make. And now I'm going to write an equation that represents this direct variation, and the equation is going to replace, for k here, I'm going to replace a 7. And I'll have y equals 7x. What that means then is that I could replace for x any number I want in terms of hours. I could now substitute in 11, and I could find out that if I worked 11 hours, I would make $77. So what I've done is I've managed to write an equation that involves direct variation. It's in the form y equals k times x, given an ordered pair. I was given that x was 5 and y was equal to 35. Let's do another example fairly quickly. Let's say that I was just given, and I pulled some problems out of your book. I'm going to look at problem number 6 in your book. Number 6 says that y equals 0.8. There's a spider crawling across my board. Y equals 0.8 and x equals 0.2. So all you need to do is substitute into that equation a value for y of 0.8, a value for k of 0.2, and solve for this k value. So we divide both sides by 0.2, and we find out that k is equal to 4. Again, the variation constant in this direct variation is equal to 4. So you can now write an equation, a linear equation for me, and that is y equals k, or 4, times x. If this were a situation, I could now plug in a value for x and find my output for y. This is an example of direct variation. Our next segment here is going to look at an application of that. Number 8 in your homework for section 5.8 reads as follows. The average weekly allowance A of children varies directly, so it tells you directly, as their grade level, G. It is known that the average allowance of a 9th grade student is $9.66 per week. What then is the average weekly allowance of a 4th grade student? So, a couple of things. They have said in the story here that it varies directly. So you know that y equals k times x is going to be the equation that you use because that's the equation for a direct variation. They've given you data for a 9th grade student. Matter of fact, they've even shown the graph. And for a 9th grade student, G, that's going to represent my x value because it's the first value in the ordered pair. They've said that their allowance on average is $9.66. So by giving you, excuse me 1 minute. By giving you this ordered pair, x is 9 and y is $9.66, they have basically said to you, develop a form of this equation by plugging in for x a value of 9 and for plugging in a value for y of $9.66 and solve for k. So I'm going to divide both sides by 9, and I'll find out that k equals, it looks like it's 1.07. Again, my variation constant. So I'm going to plug into this statement now that k value of 1.07, and I would now be able to predict for any grade X, this was 9th grade, but for any grade X, I can now predict the average allowance for that student. In particular, they asked me to predict for a 4th grade student. So I would plug in a 4 for X here, and I would find out that the average weekly allowance for a 4th grade student, and this must be some national data or something, is equal to $4.28. That's it. I'm looking first to solve for K, plug in K into this basic equation, and then sometimes use it to interpret. Number 12 in this very same section is the example that I'd like to look at next. It's about cameras and apertures. It reads, the relative aperture, or f-stop, of a 23.5 millimeter diameter lens is directly proportional to the focal length f of the lens. Please notice that it said directly proportional. That leads you to the y equals k times x equation. If a 150 millimeter focal length has an f-stop of 6.3, find the f-stop of a 23.5 millimeter diameter lens with a focal length of 80 millimeters. Now, because the last sentence asks me to find the f-stop as a function of the focal length, I believe that what I'm going to do is I'm going to let the f-stop be the value that I put in for y, and the focal length be the value I put in for x. Let's do that. So I believe I have an f-stop given of 6.3 with a focal length given of 150. Again, what I'd like to do is I'd like to call this y and I'd like to call this x, because later in the problem they asked me to substitute 80 in for a focal length and find the f-stop. And I like to have y alone. Now I really could do this the other way. It really doesn't matter. But remember, for direct variation I have y equals k times x. So I'm going to put in for y a 6.3. And for x I'm going to put in 150. And I'm going to divide both sides by that 150. And I'll find out that k equals 0.042. I'm now ready to go ahead and write an equation based on this statement, and it would be that y equals 0.042 times x. And I recognize that up here I've called x my focal length and y is my f-stop. In the problem, we've written our linear equation. They've said, what happens if you have a focal length of 80? So I need to substitute 80 in for x, and I'm going to find that I'll have an f-stop as a result of 3.36, or what I've called y. Again, I could have done this backwards. I could have put the 150 here and the 6.3 here and solved for k, and I would have had a different equation. Had I done that, however, the 80 wouldn't have been substituted in for x. It would have been substituted in for y, and then I would have solved for x. So order is not all that important here, but because I was being asked later in the problem, given this focal length, what would be the f-stop, I chose to make focal length represent my variable x and the f-stop to represent my variable y. Direct variation. Got to remember this equation. I would put that on my note card. The next type of variation problem that we're going to study is an inverse variation. An example of that is a situation. Let me share this with you. If I hired 5 people to wash the windows on the outside of the classroom building where I work, it will take them, let's say, 20 hours to complete that job. Let's say that I decided that wasn't quick enough. I wanted that work done faster. Well, I'd have to hire more people to do that. So I'd increase the 5 people to, well, let's just say 9. As a result, those 9 people would do that job faster. The number 20, the 20 hours, would go down. Again, let's review the numbers. As the 5 people increase the number of workers, the hours, the 20 hours, will go down. So as one variable the value for that variable goes up, the other will go down. This is an example of an inverse variation. The equation that describes an inverse variation is y equals k divided by x. And like a direct variation, if I said to you, let's let y equal 12 and let's let x equal 5, I would plug those values in for y and x in this statement, and I would have 12 equals k divided by 5. And then to solve for k, as in the past, I want to get rid of that denominator, so I'm going to multiply both sides by 5. And I'll have k is equal to 60 for this inverse variation. So I'll come over here and I'll go ahead and write the equation to represent the inverse variation, and it will be y equals 60 divided by x. This is objective C in this area. Let's do an application involving inverse variation. I'd like to look at number 22 in this section, again, chapter 5, section 8. Number 22 reads, the time t required to empty a tank varies inversely as the rate r of pumping. If a pump can empty a tank in 45 minutes at the rate of 600 kilometers per minute, how long will it take the pump to empty the same tank at the rate of 1,000 kilometers per minute? Now, first of all, in the very first sentence, it says that it varies inversely, so that's your tip. However, you should know that if the flow rate goes up, that the time should go down, so that you should expect an inverse variation as well. So that's your other means of knowing that. Let's go ahead now, and some people will question, of the data that was given to me, how do I know which is x and which is y? I can say this to you, that if time is represented, time tends to be the variable that represents x, or what we call the independent variable. So in this case, I was given the flow rate of 600 kilometers per minute, and I was given the 45 minutes. I'm going to let x represent the 45 minutes and y represent the 600 kilometers per minute. The other giveaway for that for me, and actually, you know, again, it really doesn't matter. In this particular case, they do give me the flow rate, so they're giving me y based on how I've established this, and we'll go ahead and deal with this problem this way. It'll work just fine. I'm going to substitute in for y here 600. I'm going to substitute in for x 45. I'm going to multiply both sides by 45 to get rid of that denominator, and I'm going to find out that k is equal to 27,000. All right, so I'll come on over here and I'll say y is equal to 27,000 divided by x. Now I just have to remember how I let my variables be represented, and they go on to say that if we had a rate of 1,000 kilometers per minute, what would the time be? Now, if I use y to represent my kilometers per minute, then I've got to put in for y here 1,000 and solve for x. And so it looks as though I'm going to have to multiply both sides by x to clear that denominator. I'm going to put a line here so you can see our work. And I'll have 1,000 x equals 27,000. And now I'm going to divide both sides by 1,000 to solve for x. And I'm going to find that it takes 27 minutes. That makes sense to me. Again, over here I had a flow rate of 600 kilometers per minute, and it took me 45 minutes. If I increase that flow rate, then I should expect the time to decrease. So that's something that you should be looking for. We'll go on after this application to look at some other variations, direct and indirect, but the variables may be raised to powers. The only other problem you might be expected to know and complete on our test that will be available next week is situations where y varies directly or inversely as the nth power of x. So no longer x to the first power, but x to any number of powers. And this represents that situation. Y varies directly as the nth power of x. And I have pulled two examples. They are not applications. I will not ask you applications with regards to this. This is just do the math calculations. And the first example is number 30, again from this section. That problem says y varies directly as the square of x and it says y is equal to 6 and x is equal to 3. So I just like to jot that down for myself to keep things straight, and let's substitute the values in. So y is 6, it says x is 3, and it says it varies directly as the square of x, so I need to put in a 2 for n because it says the square of x. And then I need to take that value and find it. In this case, 3 squared is equal to 9, so what I have here is 9k equals 6, and I need to solve for k, so I'll divide both sides by 9, and I'll find out that k is equal to 2/3. I'll come back up to the expression that represents this situation, and I'm going to substitute in a 2/3 for k, so y equals 2/3 times x. But I have to be careful because it says it varies as the square of x. I have to put x to the second power. And I've written the equation that represents this situation, given these values for x and y, and that we have a direct variation with the square of x. Finally, our last example for Chapter 5. This is a situation where y varies inversely as the nth power of x, just like the problems we had before, where we had y varies directly and y varies inversely, but now we have the nth power of x. The statement is essentially the same. The example that I'd like to use is number 32, and number 32 says, again, let's let y equal 6, and let's let x equal 3. But let's substitute it in the same places, in the correct places. But it says y varies inversely as the square of x. So I'm going to substitute in a 6 here and a 3 here, and I again have to square that x. But now I have 6 equals k over 9, unlike the last problem. And to solve for k, I have to multiply both sides by 9. And so I have 9 times 6 is 54, which equals k. I'll come on over here and substitute that into the original expression that represents this situation. Y is equal to k is 54, over x, in this case, x squared, and I have the inverse variation in the appropriate equation that works given this data. This concludes Chapter 5. Please continue to watch the videos, review them for the situations that we've covered. A lot of material here. Way back at the beginning, simplifying, multiplying and dividing, adding and subtracting rational expressions. I then like to think about rational equations and solving for x, sometimes having 2 solutions because you have an x squared term in your problem. Then going back to sections 3 and 4, we worked with division of polynomials, some synthetic division, complex expressions, complex rational expressions, which means you have to multiply by the reciprocal of the denominator. And then we got into a lot of our work involving proportions and applications and solving formulas, and finally this variation situation. Good luck. Continue to study this material and take that first proctor test in your local testing center.